Well, I'm going to talk about my project progress report. My project is implementation of varied testing to enhance symbolic execution. Now I'm going to give some background of varied testing. Well, the symbolic execution is an efficient and popular testing approach which is able to test software and find bugs automatically. In the recent years, there has appeared a large number of symbolic execution tools. The symbolic execution is attractive because of it systematically explores program and produces real inputs. Symbolic execution works by automatically translating a program fragment to a logical formula. The logical formula is satisfied by inputs that have a desired property. For example, they execute a specific path or valid safety. From a high level, there are many two ways to generate the logical formula. The first one is dynamic symbolic execution, which explores programs and generates formulas on a per batch basis. The second one is a static symbolic execution, which translates program statements into formulas, where the formulas represent the desired property over any path within selected statements. However, the problem is when generating formulas, the DSE can introduce a significant overhead because of its path-based nature, which can seriously affect the verification efficiency and its applicability in the large and complex applications. SSE has less overhead and produces more succinct formulas that covers that cover more paths, but the formulas are very hard to solve. Hence, the motivation of varied testing, which alternates between SSE and DSE. The alternation mitigates the difficulty of solving formulas while alleviating the high overhead associated with the path-based DSE approach. Here is the example of using varied testing. The code on the left side, which counts the occurrence of the character B in an input screen. Well, the program on the left side has two power to 100 possible execution paths. If I just use the dynamic symbolic execution, and each path must be analyzed separately by the SE, thus making full path coverage unattainable by practical purpose. And how and actually, the two cases are sufficient to obtain full code coverage. There are a string of 75 bits and a string with no bits. So we can see if we use varied testing before using the dynamic symbolic execution to export the path, we can have a lot of benefits. And the varied testing contains the several steps below. Firstly, it starts with DSE, and then it switches to an SAC style approach when we encounter code that is similar to the example above. It doesn't contain system calls, indirect jumps, or other statements that are difficult to precisely reason about statically. And then once in SSE mode, the testing performs analyze on a dynamically recovered CFG and identifies a core statement that are easy for SSE and a frontier of hard to analyze statements. Then the SSE algorithm summarizes the effect of all paths through the easy nodes up to the hard frontier. The last step, varied testing then switched back to the DSE to handle the cases that are hard to treat statically. Then I'm going to talk about the approach of the varied testing. Basically, it contains four steps. The first one is CFG recover. It recovers the CFG reachable from the address of the symbolic branch. The second one is CFG reduce. It takes in a CFG and outputs candidate transition points and a new CFG, and a cyclic CFG with edges annotated with the control flow conditions. Transition points indicate program location where DSE may continue. The third step is static symbolic. It takes a cyclic CFG and current execution state and uses SSG to build formulas that encompass all feasible passes in the CFG. The output is mapping from CFG nodes to SSG states. The final step is finalize. Giving a list of transition points and SSC states, it returns DSE executors to be forked. I'm gonna get a little into more details for these four steps. The first one is CFG recovery. The goal of the CFG recovery phase is to obtain a partial control flow graph of the program, where the entry point is the current symbolic branch. In this paragraph, unresolved jump targets such as the system calls and so on are forwarded to a generic execute node in the CFG. Just as the figures on the right, it shows the form of an example CFG after the recovery phase. You can see it contains the unknown model. It is the system call. Well, the second step is CFG reduce. Once the CFG is obtained, transition points should be identified. The end result of this step is the new CFG and a set of transition. The transition points, the identified of this is that it defines the boundary of SSE algorithm where DSE will continue exploration. And how can we find these transition points? For an entry node E ending in a system in a symbolic branch, a transition point is defined as a node N such that epidom En. This means the node E immediately post-dominance node N. So basically there are two types of the transition points. The first one is the unresolved jumps or system calls. And another type is any predecessor of the exit node will be a possible transition node. And then the third step is the static symbolic. Well, given the new CFG is CFGE, SSE will be applied to summarize the execution of the multiple paths. So that's the main function of this step. I'm gonna get into more details and do more research about it in the later project. The final step is the finalization. After SSE path is complete, we need to check which states need to be forked. There are two steps. We need to gather transition points and check whether they are reached by SSE. And for the set of distinct based on their jump targets address, the transition points, it is a new. We need a new symbolic state will be forked in the finalized step. In this step, the DSE executor is created. So for the project, I have three research questions. The first one is, does vary testing reduce the verification runtime? The second one is, does vary testing increase the number of found bugs? The third one is, does vary testing improve path coverage? So for the evaluation, my data source contains two parts. The first one is that I will design some local source codes which have different features, such as it contains the a lot loops, and it's consume a lot of time. And for those content the recursions which represents those codes need a lot of system calls. And also, we are design some code contain a lot of if-else logics. exceptions, and so on, which will be representative for the different features in the code. The second data source is that I will find three open source Java program. Each of them has more than 5,000 lines code. And for the evaluation approach, well, for the locally designed featured Java code, I'll test I'll test the effect of every testing on them, mainly focus on the path coverage and the runtime. For the open source Java program I found online, I will evaluate three metrics: the found bugs, runtime, and path coverage with and without very testing. Especially for the found bugs, I'll count the percentage of bugs found by both of them. I mean, with or without very testing, to see the overlap of them. And also, I will check 10% randomly of the bugs found by very testing that are not found when I don't imply very testing, to check the false positive rate, maybe the false positive rate of the very testing. So as for the result of the first RQ, does very testing reduce the verification runtime? Well, the result is absolutely yes. I For the current stage, I haven't done some empirical study for this research question, but I've done some research to know the rationale, and also read a lot of papers to say that the answer is absolutely yes. I give an example of, also it is a code fragment. Well, for in the loop part of this fragment, the total number of execution paths required to cover a loop is 3 to the power of the length of the array. However, if I can use the SSE to combine the multipath region into one execution path, it will reduce the runtime significantly, just as the graph on the right. So this shows the comparison of the number of execution paths explored, which indicates that very testing can reduce the runtime obviously. That's the end of my project process report. Thank you.